I will now look at the mechanisms in a little bit more detail, starting with Nabarro-Herring creep. This involves vacancy diffusion through the bulk of the lattice, so shown schematically here with an initially hexagonal grain, which clearly remains hexagonal but becomes elongated as vacancies diffuse from this relatively high stress region to a lower stress region here. And in this case, the generalized equation becomes the form shown here. ANH just indicates that's the constant for Nabarro-Herring creep, which is typically the order of 10 to the 15. The power law constants, in the case of B over D, it is equal to 2. In the case of sigma over G, it is equal to 1, giving this overall equation. So that's for vacancy diffusion through the bulk. Cobalt creep involves vacancy diffusion down the grain boundaries. So in this case I've shown it as a diagonal grain, and diffusion again going from this high stress region to lower stresses here. In this case the leading constant AC is of the order of 35 to 50. We have this additional ratio of the effective grain boundary width over the Berger's vector, so it will very much depend on what size this grain boundary region is, how easy it is for diffusion to occur down it. And the constants in these ratios, B over D is now raised to the power of 3, and sigma over G is still raised to the power of 1. And overall, you've got sliding of the grain boundaries as the grains elongate under this applied stress through this vacancy diffusion mechanism. In the case of Harper-Dawn creep, we now have dislocation climb, but again this involves vacancy diffusion, this time to or from dislocations. So in this case we're showing for applied compressive stress the vacancy is diffusing towards the end of this edge dislocation, leading to dislocation climb. In this case under the tensile stress the vacancies diffuse away, leading to dislocation climb in the opposite direction. The constant here is of the order 10 to the minus 11, and you'll notice that B over D term does not exist in this particular case, so effectively the power in that case will be 0. The Harper-Dawn mechanism is only significant for material with large grain sizes greater than, say, 400 microns. Dislocation creep, which occurs at higher applied stresses, also known as power law creep. In this case we actually have dislocation glide, again coupled with vacancy diffusion, and it's actually that vacancy diffusion which enables the dislocation to get past obstacles. And different values of this power n are reported for different materials. A couple of examples of oxides, namely aluminum and magnesia, where n equals 3. Something like sodium chloride, silicon carbide or uranium dioxide, n is found to equal to 5. And if you've got a dispersion strengthened alloy, n is actually greater than or equal to 7. Dislocation glide occurs at higher stress levels and is not dependent on diffusion, and effectively this is the same as conventional deformation at room temperature. So we have a range of different mechanisms, and these can be summarized in a Workman-Ashby map. So what we are plotting here is sigma over G, the applied stress divided by the shear modulus, versus the homologous temperature, and I've shown the particular case for tungsten with a grain size of 10 microns and a dislocation density of 4 times 10 to the 10 centimeters to the minus 2. We'll see that we have various regions marked. Cobalt creep, which is where we have diffusion down grain boundaries. Nabarro-Herring creep, where we have diffusion through the bulk of the material, or tends to dominate a higher homologous temperature than cobalt creep. Then as we go to higher stresses we see dislocation creep, and then finally dislocation glide, and this line essentially indicates the theoretical strength that you would achieve under shear if you had no dislocations, and of course we never normally achieve that theoretical strength value. So that's the map for tungsten with grain size of 10 microns. You can actually add to that map strain rate contours, which I've done here. So this is all data from the redrawn from the literature, and you can see various contours going from 10 to the minus 10 seconds to the minus 1 through 10 to the minus 2 seconds to the minus 1, for different strain rates. The other thing that you can find is that the grain size actually affects the position of the boundaries on this map. So here I've drawn the equivalent data for tungsten with a 1mm grain size. So you can compare these two maps for the same basic material but with different grain sizes. Clearly there are some significant differences in where the boundaries are drawn on these two maps, but they are both Workman-Ashby maps for tungsten. So using those two maps, I'd now like you to work out for a tungsten filament light bulb with an operating temperature of 2700 degrees centigrade what the creep rate is at a stress of sigma over G equals 1 times 10 to the minus 6 for the cases of the filament having a grain size of 10 microns and 1mm. So you should have a go at that calculation before moving on to the next video.